meeting together in the headquarters of the BBVA Foundation in Madrid in order to deliberate and decide. The committee has resolved to grant the BBVA Foundation Frontiers of Knowledge Award in the Basic Sciences category in its 16th edition to Claire Voisin and Yakov Eliashberg for their outstanding contributions to two phases of geometry, algebraic and symplectic. The spaces in algebraic geometry are defined by solutions to algebraic equations using complex numbers. Those in symplectic geometry are generalizations of the phase space which describes the state of a physical system. Both types of geometry involve spaces of high dimensions which are difficult to visualize and which necessitate new mathematical techniques to understand and study. Voisin's results in algebraic geometry have shed new light on the role of Hodge theory and led the subject into new realms of activity by her work on hyperkähler manifolds. Eliashberg extensive results in symplectic and contact geometry gave in particular a topological characterization of Stein manifolds and the identification of a dichotomy between flexible and rigid aspects of contact manifolds. The two areas of mathematics have been reinvigorated in recent years because they relate to quantum field theories studied in theoretical physics. Their roles are interchanged in that context by mirror symmetry. Voisin and Eliashberg have played essential roles in developing these different aspects of geometry, in particular by adapting concepts from either side, crossing the boundary between the two disciplines. Their work has inspired a high level of activity of international research in both areas of mathematics.
What would you say has been your most important contribution to algebraic geometry?
It is hard to choose because I think I contributed to various aspects of algebraic geometry. Now, because the prize emphasizes the relationship between algebraic geometry and symplectic geometry, maybe I will mention first my construction of compact Kähler manifolds, which do not have the topology of projective complex manifolds, because that work sits between algebraic geometry and compact Kähler geometry, which is the compact Kähler geometry is exactly the geometry which sits between complex projective geometry, that is algebraic geometry, and symplectic geometry. So, of course, there are other aspects of my work that are much more inside algebraic geometry, like my work on rationality questions and my work on smoothability of cycles, recent work with Collar, but maybe let's just mention this one.
Could you explain how your work has been instrumental in building bridges and crossing the boundaries between algebraic and symplectic geometry?
First of all, I have to mention that the first bridge between algebraic geometry and symplectic geometry, as I mentioned, this bridge is very natural. It is due to the fact that complex projective varieties are scalar, and because they are scalar, they are symplectic. But this bridge has been emphasized and systematically explored first by Gromov. As I mentioned, my work in compact scalar geometry is a contribution to this to the study of the relationship between these two geometries. But also there is a whole set of questions that I studied myself, but which has been also studied by Deza Magdeuf or Yongbin Ruan and collaborators, and also Janos Kolar, which ask which properties of a complex projective varieties are of a symplectic nature, that is, depends only of it as a symplectic manifold. And for example, I worked on the question whether rational connectivity is a symplectic property, a question that is still open, and which I worked in dimension 3. And I also worked a little on mirror symmetry, that is a marvelous set of conjectures relating the two geometries. But that was a very long time ago, and my contribution was maybe not very major in that domain.
How would you define the value of your research in mathematics for society?
It's a hard question because, of course, my work is not at all in applied mathematics, so there are no direct applications. Still, I mean, what you do in your field, in following your own interest, it has an impact on people around you, and then it has always unexpected applications that you cannot predict. People use your work in one way or another one. It's hard to explain how it works. But certainly, the mathematics is a whole, and what you do may have some more influence than just your small world. But there is another aspect that I consider as very important, the fact that for me mathematics is important not only through applications to other sciences, but for itself as part of our civilization, because mathematics defend a certain way of thinking, the rigor, the fact that for us a statement is not a true statement if it is not proved. I mean, it's of course as a sort of a definition of mathematical thinking. So I find this, we defend that it is very important to prove a statement, and in itself I find it important. And the last point I consider also as very important is that our work needs a lot of concentration and learning the discipline that gives you this concentration. It is for me something that is I mean, we can communicate to the society the fact that we need concentration to work, and that is essential to our work. And concentration, it's like meditation. It's a way of being. It's something that you need to learn as a practice.
What would you say has been your most important contribution to symplectic geometry?
I was lucky to be present at the birth of the subject of what is now called symplectic topology, along with such great mathematicians as Misha Gromov, Andreas Floer, Helmut Hofer, Duze McDuff, Claude Viterbo, and several others. One of my joint and independent result with Misha Gromov, so he proved a different way and independently, was a proof of rigidity, C0 rigidity of symplectic diffeomorphism, and this result established existence of the subject of symplectic topology. Later, I was working a lot on contact geometry, which is a odd-dimensional sister of symplectic geometry, and one of my maybe important contribution is in the introduction of dichotomy of contact structure into tight and over-twisted, which was instrumental in the development of the subject. And finally, I'll mention our joint work with Helmut Hofer and Alexander Gevental on symplectic field theory, the subject which is still developing and I hope will be more and more important.
Could you explain how your work has been instrumental in building bridges and crossing the boundaries between algebraic and symplectic geometry?
Symplectic geometry, so algebraic geometry was one of the sources of symplectic geometry along with classical mechanics. But symplectic structures are much more flexible, so in symplectic world you can do constructions which are impossible in algebraic geometric world. And it is important to know this boundary between symplectic rigidity and flexibility, and I was working on establishing these boundaries. So also later, this interaction between symplectic geometry and contact and algebraic geometry were enhanced by the mirror symmetry conjecture coming from string theory, which were saying that certain object and result in algebraic geometry can be interpreted as a result in symplectic geometry and object in symplectic geometry and vice versa. So I never worked directly on mirror symmetry, but I think that certain structure which I introduced, like in particular coming from symplectic field theory, were important for understanding these connections.
How would you define the value of your research in mathematics for society, both in terms of advancing basic knowledge and of developing possible future practical applications?
So mathematical subjects, even if they arise from need of some outside world or outside sciences like physics or biology, they never follow their development follow their own path. So mathematicians create their own worlds and explore these worlds. They bumped onto abstraction in this world and finding some hidden path, and sometimes this path leads to different subject and connection with completely unexpected mathematics, or sometimes not even mathematics but other subject. And in the best case scenario, it really spills to some fantastic application to outside world. And this is in some sense already start happening with symplectic topology. So, for instance, it was originally dreamed by Poincaré as a tool for answering qualitative problem of mechanics. And right now, there are a group of mathematicians working in symplectic topology who, in collaboration with NASA scientists, and they are trying to use this recent progress and development in symplectic topology for designing more effective space missions. So I don't know what kind of my work may bring, but I hope that it also can contribute to this development. I also want to say that the part of my work as a professor at the university also is upbringing of and new young mathematicians and scientists, and many of them brought up on kind of very good mathematics. They go to outside world and contribute in many ways, maybe which I couldn't even envision.